Leslav Rachel, also here. If I will follow the timetable, then I must ask you to formulate questions first to Professor Butkevich, who has a talk on semi-explosive cross-sections for charged current, quasi-elastic and neutral current elastic neutrino scattering of 40 argon and the sterile neutrino oscillation study. Have you questions to him? No? Then I'm
sorry. I have a question to speakers who talked about dark matter. No matter whom, but preferably Professor Arbuzova. Are there some indications for superluminal particles in dark matter?
No.
Сверхсветовые частицы. No experimental evidence. Like
but are they considered in theory?
In our theory, we do not consider particles with velocities higher than the velocity of light speed.
So you don't know examples of some authors who consider such particles? Is it correct?
We do not consider such particles.
I know you do not consider, but maybe someone, not you, but someone else.
I don't know. No.
You don't know. Okay, good. Thank you.
Can I comment on this?
There are some papers on tachyonic particles, but they are usually pathological and unstable.
Can I just?
I mean, I'm sorry. I do not mean tachyons, but I mean super bradyons. There are such particles which are called super bradyons.
Yeah. If I might comment, the case for dark matter that is made is from studying galaxies, clusters of galaxies, and cosmology. And in every one of those cases, the dark matter that is relevant is traveling way below the speed of light. In fact, it's even called cold dark matter for that reason. So as far as dark matter is concerned, there was never any issue of superluminal flow. Now, what I think the question is asking is those theories which generate dark matter candidates such as WIMPs, could they at the same time be generating particles that travel faster than the speed of light? I think that's the question, which is a theoretical question in and of its own. But if you talk about machos, and Dr. Dolgoff discussed that in great detail, those machos do have irregular masses and are traveling below the speed of light. So I don't think you have any chance of macho dark matter being superluminal, but maybe some of these mysterious things that are being evoked for the WIMPs, some of them might turn out to have a superluminal component. I don't think that's being excluded. I'm just not aware that anybody has ever emphasized the point.
Can I ask a question to?
I'm sorry, just a minute. The matter is that super bradyons are particles which can move either faster than light and slower than light. They have a potential ability to move faster than light, but not necessarily they really move faster than light.
But they can't cross the light cone. I mean, as I understand it, particles traveling faster than light cannot cross the light cone. They're in a very specific region of the space-time and can never get out of that region. much the same way as
Yes.
photons on the light cone are never inside or outside. And I think
I know that in Einstein's theory they cannot, but there are alternative theories which let particles cross the light cone.
Oh, okay. I'm not sure.
Alternative theories, non-Einsteinian one, which allow particles to heavy particles to move faster than light.
Professor Kiselev, would you like to ask question?
Yes, I have a question to Elena Arbuzova. You mentioned in your talk a possibility to detect some effects in high energy cosmic rays from very heavy X particles. My simple question is, did you try to estimate possible flux of these particles, maybe just to estimate if this flux is diffuse, or maybe you have some ideas of the value of this flux, because if this flux is negligible, it will be very difficult to detect such particles. Okay, thank you.
Our investigations were stimulated by the observations of extremely high energy cosmic rays higher, with energies higher than the limit of Greisen-Zetsepin-Kuzmin. So there are some events in the spectrum of the high energy cosmic rays, and we wanted to suggest a mechanism from where such very high energetic particles could come. So now we want to calculate the flux from the of high energy cosmic rays from the annihilation of our X particles, and now we work on the estimation of the energy flux in these processes of annihilation.
Okay, thank you. It'll be interesting to get such
I wanted to make another comment. Distribution of dark matter around galaxies demonstrate flat rotational curves, and I don't think it is possible to make flat rotational curves with superluminous particles. And anyhow, any form of bound system of galaxy and this very quickly moving dark matter.
I have a question to
Can I just comment on that comment? The whole point of
I'm sorry. It was told that cosmology is modified in the model presented by Elena, and I would like to ask simple question. When we usually see the simple picture of time evolution of the universe, very well-known picture, how much this picture will be changed in this theory? And I understand, or maybe incorrectly, that the radiation epoch is absent, and meta domination is started from the very beginning, or I'm not right?
We suppose that firstly it was inflationary stage when our universe expanded exponentially, and curvature scalar tends slowly to zero. But when curvature scalar approached zero, it started to oscillate, producing particles. And at this moment, particles are produced, and maybe it is possible to call this time Big Bang, like Big Bang, universe heating. So the universe stopped to be a void of matter, and it was filled with particles. At what time? At how many seconds? Where and in seconds, you know. Which redshift? Mm. Yeah, difficult question. Simple questions are always very difficult.
Sorry. And maybe someone would like to ask, for example, Professor Mannheim. Are there any questions to him? Vladimir Petrov?
Yes, I have. Have I heard? Professor Mannheim, do you hear to me?
Yes, I do now. Yes.
Okay. Now I want come back or forward maybe to Professor Mannheim. And, my question is, normally, if I take, for example, the axiomatic approach, there people normally in a kind of axioms, and among these axioms, the first one is the proposed existence of the normalized vacuum state. With all other axioms, do you believe that from your consideration, such a system may be contradictory because it doesn't take into account your arguments about normalizable vacuum?
I would say the following. The axiom of field theory that a sensible field theory has to have a well-defined ground state, I do not dispute, and I think and every theory I've worked on has that. However, if you look at a book like Streeter and Whiteman, PCT, spin and statistics, and all that, on page 1, they state that the Dirac norm of the vacuum is finite. And they only consider those theories where you're looking at a 2-point function, a 3-point function, let's say phi between the vacuum and its Hermitian conjugate. Everything that they do is done within that framework. They never at any point ever show that the Dirac norm of the vacuum is finite. And that was one of the things that I started to look at. But I think that their statements are still correct in as much as once you've got a good inner product, you do have a proper Hilbert space where you can then explore axiomatic quantum field theory. But you have to, you can't assume the Hilbert space. You have to show that the quantum theory has that Hilbert space. And the big surprise that Carl Bender and I identified in higher derivative theories is that the obvious Hilbert space is not the right one.
Yeah, but normally they do not deal with Lagrangians with derivative or without derivative. So the question is, again, I repeat maybe a little bit. So am I safe if I take any set of axioms which usually are used that I can may postulate without any reservation the existence of the normalizable vacuum, or I should take care about something else which is not usually discussed?
That's what I'm claiming is that it's a hidden assumption and you have to check it in every case. And I gave a simple way to check. Either the path integral exists or it doesn't. And that's a way to check. But I'm stating that you can never assume that the state that you have introduced as the eigenstate of the Hamiltonian, which is the lowest energy state, that's safe. You can never assume that the overlap of that ket with its Hermitian conjugate bra is necessarily finite. You literally have to go in and show it every time. And what I presented in my talk today was a procedure for doing that. Now, the good news was that also the second order theories, this is not a problem. But the bad news is that for fourth order theories, this is a problem. But that turns out to be the good news because that's what saves the fourth order theories. You just have to, you're in the wrong, the problems that you think
So
you
I
have
conclude
are in,
that
are in the Hilbert space. Yes.
So I conclude that anyway, some care is necessary. Anyway.
Oh yes, yes, absolutely, yes, yes.
Maybe I will ask to say some words by Professor Shapiro.
Yeah, just a second. Okay, I have a few questions to Professor Krasnikov. And the first is, some are like related to his talk and some are just because I did not get what he was saying. Why the Landau pole means unstable vacuum?
I'm sorry, but he is not here.
So I'm unlucky. I wrote 5 questions and had no time to ask anyone. Okay, thank you very much. I'm sorry.
Can you write him email? Can you write him?
Yeah, sure, Vladimir. Okay, thank you.
Ilya, I thought a Landau pole is loss of unitarity, not loss of stability.
No, what he was saying is that Landau pole means that the vacuum becomes unstable. Okay.
Oof. Oh.
Thank you.
Thank you. And Professor Teryaev, you have a question?
Yes, I have a question to Philippe Mannheim. Just hello, and I have very simple and naive question concerning. You started from oscillator, right? What
Yes.
about commutation relations? If you take the commutation relations with the just unitary operator in the right hand side, how can they correspond to normalizable state?
Okay, the commutation relations don't tell you anything about the states. You have a commutator, let's say of A with B,
Yeah.
they're operators. You
Yeah.
have to know on what states they act
Yeah.
before you can call them operators.
Yeah.
So specifying a commutator doesn't specify a quantum field theory.
Yeah.
That's basically what I'm saying. And you have to do some more work. But nonetheless, you will find that when I'm through, the canonical commutators are the canonical commutators. I don't change them.
Yeah.
They stay as you think they are. However, what they act on has to be determined by boundary conditions.
Yeah.
And so canonical commutators don't tell you anything about boundary conditions.
But what I mean is, of course, a very simple exercise that if you take the commutator with unity operator on the right hand side and you switch this between the states, say vacuum, any normalizable state, you have a contradiction. You have 0 in the left hand side and you have something in the right hand side. And usually this is an argument, for example, that there are no normalizable eigenstate of momentum and coordinate operator. Okay, but so in order to make the state normalizable, would it mean that we should abandon the commutation relations with unitary operator on the right hand side?
No. What you're asking is, if you think you've got a non-normalizable state, and then I'm telling you that there's another Hilbert space where it's normalizable, you can't go from Hilbert space 1 to Hilbert space 2 by a unitary transformation. They just don't exist, because you're trying to go from one Hilbert space to another. And that's what somebody asked me earlier on about Haag's theorem. It's just not, it's not there. They're not unitarily, the Hilbert spaces are not unitarily equivalent. The commutation relations are. The commutation relations you can transform as operators with unitary transformations, but not the states. And that's the important point. Because you've got to, in the end, you've got to know about boundary conditions.
Okay. Thanks for these interesting points.
Yeah, let me say this.
I have to think more about it. Thanks.
Can I say this? I didn't invent any of this. Carl Bender did. I just applied it to fourth order theories. I mean, Carl and I did it together, but he developed this whole apparatus of antilinear symmetry And what I eventually showed was that a theory is well defined if it has CPT symmetry, and that's more general than hermeticity. Hermeticity is the special case.
I see.
And CPT symmetry, I've proven, is the most general case.
So this means that you should be very careful in taking matrix elements of commutation relations, right?
Absolutely, because you first have to. Another way of saying it is this: when you apply a commutator, you apply it on a test function. Now, the test function is square integrable. That means you've already constructed the boundary conditions to know that you have a good test function.
This is more or less what I mean in my last statement. Okay, to do it very carefully. Okay, thanks. Thanks, Philip.
Is Professor Petrov?
Yeah. My question is because it seems to me that it is with us, Alexander Zakharov. Yes? Is it here?
His icon is here.
Zakharov, he is on the list of those who would be listening to us, but actually I think he is absent. He just forgot maybe to switch off his presence. Okay, thank you. No person. Okay.
So everybody, I think, can see who is here. And so, please, any more questions to any speaker?
Yeah,
a question to Sergei Slabospeitsky concerning a talk on Quarks. I'd like to ask about hadronization of Quarks. Let's imagine situation when we produce quark which moves with very high velocity, so that it can travel macroscopic distance before it decays in its conventional decay mode. In this case, do we see hadronized quark according to confinement, or we will see quark with a charge 2/3 of electron charge?
Good question. If I will be really honest, I should say I don't know. Because it's a very good question. You know, we can, for example, why we consider top quark? Let us consider the B quark. The quark, it's slightly high. Let us assume that we produce a big quark with the energy about 1 TeV or 10 TeV. And then we can apply the same arguments, and we should expect the appearance of the real top quark in the final state, but it's not true. So from my point of view, the top quark should anyway will not produce as a real object. In any case, it should decay. And if you consider this equation, it seems to me that anyway it starts to hadronize, but its decay time will still less than hadronized time, because if you use your question, your language, in this case, I should also, in some sense, consider that the hadronization time is also increased. So that anyway, top quark will decay before its hadronization. It's my understanding. I'm not sure that my understanding is correct. It's my understanding of this problem.
I suggested to consider an extremal limited, some limiting process, extremal situation where hadronization and confinement properties are isolated in some sense.
What do you mean isolated?
Look, we can consider confinement as it is. we can discriminate between time of hadronization and distance of hadronization. These are different concepts.
But this is not Lorentz invariant parameters.
It's
Let me
Yes,
let me propose you another absolutely different interesting situation. Let us assume that we have a neutrino which interact with the cosmic proton with energy, for example, 10 to the 50 TeV, and in this case, this huge neutrino interacts with proton. In this case, we can produce a up quark, like with charge cousin interaction, and this up quark will have the energy at about 10 to the 50 TeV. Does it mean that we can observe a real top up quark because it's stable particle?
Oh, we, as our experimental observation.
No. Let us start to continue the consideration in your language.
Yes, when up quark move with ultra relativistic velocities, they are confined, and we don't see light quarks as isolated objects. We only see hadrons.
Yeah.
However, the decay time of up quark is not well defined concept. And even in the case of big quark, it is not well defined. However, in the case of T quark, it seems to be well defined concept. The lifetime of the T quark as it is.
Strictly speaking, I have no exact question. My understanding, I can repeat, that the process of hadronization will, first of all, if you wish to consider the top quark produce very ultra-relativistic case, I think we need to rewrite all consideration concerning confinement in relativistic Lorentz invariant language. I have no another explanation. So because in this case, the decay of the top quark will be different from another system to another system. So in the history of the top quark with this zero velocity will be absolutely different from the history of the top quark with huge energy. But this is not true. The history is unique since we are believing in Lorentz invariance. No, it's a very interesting question. I think for the moment I have no ground ideas. I have no ground explanation. Maybe Andrei Kataev is here who can give some comments for that. I don't see a Kataev. Okay, sorry.
Sorry, I'm asking about questions from the participants from the Zoom. Have you any?
Yes, hello. Can I give a further comment to Dr. Teryaev? Basically, what you're asking is this. Suppose you have commutation relations 1 and commutation relations 2 and are the same, then they're unitarily equivalent. But the way it works is very strange. You have vacuum in the new commutator, overlap with the vacuum in the new commutator is 1. You then put inside U dagger U. So you have vacuum, U dagger, U vacuum. Now, in between the two U's, you put in the sum of a complete set of states in the previous vacuum. Now, every matrix element, new vacuum, unitary operator, old state is 0 because the Hilbert spaces are different. But the sum on them gives 1. In other words, it's a very special limit in which 0 times infinity equals 1. So the way that unitarity appears to be held is because you're summing over an infinite number of intermediate states, all of which are vanishing, but they're vanishing at the same rate as the number of them is increasing. And that's basically how Haag's theorem works. Does that answer your question? I don't know if he's there. Well, If not, I have a question for Dr. Dolgoff. I believe he's in the auditorium. Is that right?
Yes, he's here.
Yes. One of the things I found puzzling about the issue of primordial black holes as dark matter is you seem to suggest that you wanted to have 10 to the 22 gram very light primordial black holes as the dark matter in the Milky Way. But later on, you discussed the possibility that even 100 solar mass black hole could also be primordial. So then the question is, who decides which particular range of black holes populate the Milky Way? How does it get to be that if there's a whole range of allowed masses for primordial black holes, why is there a specific set of masses that is preferred within the Milky Way, if that's to be the explanation of galactic rotation curve?
Well, according to our model with log normal spectrum, we know more or less homogeneous distribution of black hole dark matter over all galactic halo, that is somewhat larger radius than the Milky Way, and there could be there also could be something like excess of matter at the center of Milky Way. I am speaking in the same, it is the same picture as normal dark matter. It does not matter if the mass is 10 to power 13 JeV or something like that, or black holes with masses typically 10 solar mass. So we have normal distribution with density going down like 1 over r squared, which goes to flat rotational curves. And in the center of the galaxy could be something like, how much is it? There should be a kind of spike with larger mass density, which could be something like, as far as I remember, about 1000 JeV to power 4. It means more or less normal stellar density, so slightly in the center of Galo, which is a couple of orders of magnitude higher than the average density. Nothing in particular. It's like it doesn't matter what kind of objects, either light, what is this, beams or huge matches. It's
I'm sorry if I haven't followed everything you just said. I'm not disputing the possibility that there are heavy black holes in the center of the galaxy, but they are not going to produce a flat rotation curve in the periphery of the galaxy. They're just going to lead to a 1 over r fall off of Kepler, but with a bigger coefficient. If you want to produce flat rotation curves, you need dark matter in the outskirts of the galaxy. Moreover, if you want the dark matter halo to stabilize the galaxy, which is because a Newtonian disk is not stable, you need it to be in a spherical halo. So if you are going to put very massive black holes in the spherical halo, they should have been detected in the Macho experiments, and they weren't. So I thought that you were saying at the beginning, therefore I want them in the halo to be very light.
Oh, well, it is not so. Black holes with masses of 10 solar masses behaves exactly like normal dark matter in all respects, but their number density is very small. So Macho microlensing is not very sensitive to that. You have to catch black hole, and what is this? If I have 10 something like 1 kilo electron volt per cubic centimeter, 1 keV is something like 10 to minus 30 grams. So the distance between black holes with masses 10 to power 10 to power what is this, 10 solar masses, we can estimate it is something like 10 to power 34 grams, and we have to take this average distance to take 1 keV per cubic centimeters. There are very rare black holes in the galactic halo and slightly more in the center. So it is much is not sensitive to that. With much experiment by microlensing, there is a kind of unusually high density. They look at the Magellanic Halo and maybe there is some enhancement of these very strange black holes. And in our model, typical black holes, 10 solar masses, and there is huge distance between them. So it's very difficult to find by micro lensing of such black hole. In principle, it's a good idea, and it was, I think, at a conference either by Besnavati Kogan recommended to search for this experiment.
Okay, if I just may summarize what you said. Initially, I thought you were arguing that they would be 10 to the 22 grams, which of course would.
Sorry, say it again, please.
Yeah, they would escape microlensing. That I'm not worried about. But then later on, you started to say, well, there could be much heavier ones. And then the question is, there's a window for microlensing where you could not have seen a black hole even if it were there, but it's not an open window. I mean, you seem to have a complete range of masses of black holes, and therefore some of them would fall in the window if they're in the halo, in the microlensing window. They're in the halo.
There is log normal distribution with a peak around 10 solar masses, 15 solar masses. Yeah. So that, and if you go by order of magnitude outside of that, there is strong decrease in number density.
Yeah, but you compensate that by just looking longer and longer. You just keep observing the LMC until you see something.
And what?
I mean, if it's a lower density, you just have to keep looking longer. I would have thought. I mean,
yeah,
maybe they haven't. Maybe they haven't looked for a long time. Maybe that's the reason.
Sorry, can I interrupt you?
So there is nothing in particular, and the direct method doesn't work.
Maybe we will let him possibility to say something.
Okay, do you hear me?
Yes.
Do you hear me? It's just I would like to continue a discussion about microlensing because we published a couple of papers with Sajan and individually I published something. You have to keep in mind that our knowledge about microlensing results is very poor because there is degeneracy between distance and mass of microlenses. And practically, usually people do not know masses of microlenses. Bogdan Paczynski, one of the pioneers of these studies, he said, if we assume something like salpeter mass function, we could something like evaluate of parameters of salpeter mass function for microlenses. But in this case, we need at least 1,000 events. Toward Magellanic clouds, we have only few, dozens, but not thousands. So in this case, there are a lot of assumptions. Moreover, we don't know masses really. It's based on assumption about, let us say natural, but we don't know distribution, mass distribution for, let us say, for dim stars. Practically it's assumption. But moreover, about microlensing and black holes. Around 20 years ago, microlensing people said they discovered microlenses with masses which much heavier than Oppenheimer-Volkoff limit. In this case, they even proposed to observe, since there is it has to be accretion, it's possible to detect this kind of object with Chandra or XMM X-ray satellites. But practically the people got observational time, but they found nothing. It means you have to keep in mind always that there is degeneracy, mass, and the rate distance relation between these two parameters. But also some historical remark about general relativity and Schwarzschild solution. Very often, including Alexander Dmitrievich talk, people are saying Schwarzschild found his solution almost immediately after GR discovery. But you have to keep in mind that Schwarzschild solution is vacuum solution of Einstein equations. But gravity equations were found by Einstein and Grossman in 1913. So it means Schwarzschild had much more time, a few years, to find his solution. And also, Alexander Dmitrievich, I wrote you some email also with references concerning other issues which could be discussed. Thank you.
Okay, Alexander Fedorovich, thank you for your comments. As for matches, it's indeed a rather mysterious thing. For example, what is strange, they are observed only in certain directions, and it probably means that they have inhomogeneous distribution, if they exist. And I agree that they are quite mysterious, and thank you for the reference. I should mention paper by Sajan that you told me about some time ago. Okay, thank you again.
Thank you.
If I may make a comment on the Schwarzschild solution, as I understood it, Einstein was trying to generalize the second order Poisson equation, not the second order Laplace equation. So he was really interested in how the geometry outside of a source is fixed by the structure inside the source, which is the standard second order Poisson. He didn't look for a vacuum solution because the one that Schwarzschild wrote down was actually a cheat. I mean, he gets that G00 is 1 minus the constant over R, but he had absolutely no basis for saying that the constant was related to the mass of the source. You don't get that until you match to the interior solution. So he just said, well, let it be the mass because I know about Newton's law of gravity. But he never ever derived that the coefficient of the 1 over R was in fact the integral over the energy density of the source. That only comes when you try to match to the interior, which is what Einstein was doing, only he was doing it in lowest order because he just wanted to get the second order Poisson equation and get the V squared over C squared, which is what he got, and which is why we get the perihelion of Mercury.
You're absolutely right, but I would like to keep in mind that what about Einstein and the Grossman result? They are saying that Ricci tensor is vanishing for vacuum. That is their main result in 1913. Practically, Schwarzschild was solving this, let us say, relation, not because he did not consider, let us say, matter in his consideration. It's possible to avoid matter, absolutely. So no matter. It's vacuum solution. In this case, you do not need stress energy tensor to consider vacuum solution. Not at all.
No, when you solve it's not a vacuum, it's an exterior solution. When you solve the exterior solution, you get integration constants. You can't fix them until you couple to the source. I mean, the integration constants are just, you just got a second order differential equation. You get 2 integration constants. One you set, you fix by saying that the geometry is asymptotically flat. So that's the one. And the second is you say that the 1 over R term, the coefficient is mg, because you know that's how it works for Newton. But that doesn't follow from saying that the Ricci tensor vanishes outside a source. You absolutely have to know what's going on inside the source.
Okay, I have to think, but I'm not sure that you are right. But because it's in principle, you know, it's because it's also very misleading terminology because Schwarzschild derived one solution, which later Drost said it's possible to rewrite the solution, and after that Hilbert rewrote this solution. In this case, we know this interior and exterior solution, but Schwarzschild has no interior solution at all because he used another coordinates.
Yes.
So,
No. Schwarzschild could have solved the problem in isotropic coordinates. I mean, and you can make a coordinate transformation from the Schwarzschild solution to the isotropic coordinate system. I mean, we know the solution. It's a little bit more ugly, but we definitely know it. But saying that the geometry is Ricci flat is telling you that some second order derivative function of the metric is 0. And you can't say any more about it. You can say the generic form by integrating the equation, but you can't say anything about the integration constants. That's all I'm saying.
Oh, okay. It's I have to think. It's okay. Thank you.
All right. If I may be permitted to ask a question, I wanted to ask Dr. Arbab 2 questions actually. Are you there?
Yeah.
Okay, good. The first question was, you wrote the telegraph equation. Now, if I take the Klein-Gordon equation and I replace psi by e to the imc squared t over h bar times psi, then the d2 by dt squared generates the first order d psi dt term that you wrote down. So isn't the telegraph equations, I mean, I may have got it wrong, I only scribbled it out on a piece of paper, but isn't the telegraph equation simply a transform of the Klein-Gordon equation?
You are right that the equation for the curvature scalar is similar to Klein-Gordon equation. Yes, it's very similar.
Yeah, but the transformation, you let psi go to e to the imc squared t over h bar times psi, is not a conformal transformation because it's a complex phase. It's not a real phase.
What transformation do you mean? I don't understand.
The wave function solution to Klein-Gordon, you let psi go to e to the imc squared t over h bar times psi. And I think you get the telegraph equation. But that whatever you get, that's not a conformal transformation because of this e to the imc squared and not e to the mc squared. That was all I was saying. I mean, I'm not saying you've done anything incorrect. I was just saying that I found that a little bit puzzling. Okay. Can I give you another comment? Okay. Early on in your talk, you took the Einstein tensor and you transformed it in a geometry, in a Robertson-Walker background geometry, and you generated a g mu nu term and a delta mu 0 delta nu 0 term. Now, my question is, when you did that, were you using an arbitrary conformal transformation or a very specific one? And maybe I can...
Well, whom are you asking?
Yes.
Dr. Arbab, yes.
Yes, Dr. Phillips. I'm using a very special case to get that result. Only where the conformal factor goes like E, we see some constant T.
Can you say it again? How does the conformal factor behave?
It behaves like exponential function E raised to some alpha T or some constant.
Okay. Well, alpha is a constant.
It's a constant. That's only very
specific yes, problem. That was one thing. Maybe I didn't hear it in the talk. You must have made a very special conformal transform.
That's very special, and that could be choosing some direction in time, just like Friedman. In Friedman cosmology, also you only take the time direction and you forget about other special.
Yes. Okay. So I now think I understand what you did. If I take the Robertson-Walker geometry, I can write it as conformal to flat.
Yes, that's true. Yes.
Now, if I could make a conformal transformation which would kill the conformal factor altogether, and then I'd finish up with flat. But you didn't do that. So what you did, you took the metric, you took the Einstein tensor, and because you've transformed the geometry so it's still conformal to flat, you must get the Einstein tensor becomes the form of a perfect fluid. So it has to have a g mu nu term, and it has to have a delta mu 0 delta nu 0 term, which is exactly what you found. But that doesn't tell me what the coefficients are. That just tells me the generic form.
Yeah, that's true. And in that case, one could also relate the scale factor to that omega especially during inflation.
Oh, okay.
That could be a particular solution of the Friedman equation during inflation. So during inflation, this could be the way how the mass is acquired. So one could also say that before inflation, if the field were massless, then mass was created during inflation period.
Well, that may be, but in inflation, the conformal factor is not e to the alpha t.
Mm-hmm.
The co-moving
in a co-moving frame,
factor is e to the alpha t.
Yeah,
but when you put it out, you have to transform dt to dt over alpha.
Yeah.
And that gives you a conformal factor, which is just t itself.
Yeah, yes, I agree. Yeah, that dt goes to over eta, some conformal parameter.
Okay.
You are totally correct. In fact, it is just a recent work that I have just started, but such a kind of comments will help me, do more work later on. Thank you very much.
Good, very good.
Okay, thank you very much for your discussion. And it seems to me we should close. Thank you all the participants again. And
I'm sorry, just a second. I have typed 3 questions in chat. One of them I have asked here, and 2 of them are stayed unasked. Maybe someone can answer these 2 questions in chat.
everybody can enter the chat and answer your questions. Thank you. But today we should close. Thank you very much. Goodbye.